Guys, you need to know about quantum mechanics. This is going to take 20 minutes of your time, and who better to learn it from than a quantum physicist? So, let's learn together.
So one of the nice things about waves is it's the first encounter in a physics course where you start to realize the interconnectedness of maths and physics, and it's very dynamic, okay?
So Henry's just explaining why waves are important. Waves are used for transporting energy and everything that makes up our world. It's all just an interaction of waves.
And x could be, some kind of distance, okay? So it's a position, okay?
So here he's mapping a function. So a function is just a way of simply graphing information. So you could think of this more as a map, a geographical map.
The position. So if, we're over here, there's not much height, and then as we go further, we reach the peak of some kind of mountain, and then it flattens out again, okay? So that's very nice. So once you have functional analysis, you can start mapping out.
You could always think about this as mapping a mountain as well. So it could be in 3D or 2D space, it doesn't really matter. It's just more thinking about how we can visualize a wave, because they're quite abstract ideas.
So it's like a cartoon. But what if we have a more complex phenomenon, okay? So I'm going to go ahead and draw it, and then I'm going to show you what it is physically, okay? So, again, I'm going to do height, okay? And I'm going to do it as a function of time, okay? So let's do time. And this function, it's going to look like this, okay? So mountain, but then a trough, and another mountain peak, and another trough. And it's what's known as periodic, okay? So if I start here, I can get back to the same height here, okay? But notice here I'm moving upwards and here I'm moving downwards. So in order to come to the exact same position, I have to be here, okay? So this length, okay, is going to be known as the length of our wave, okay?
So this is just a basic anatomy of a wave. So we've got the wavelength, which measures the width. We've got the peak, the highest point. We've got the trough, the lowest point, and the rest position in the middle. So this is just a basic way of understanding all the different parts of a wave and what we're looking at on a graph.
A wave phenomenon. So it's periodic. Even just moving it about like this, you can see that there's a wave phenomenon happening, okay? So it oscillates back and forth. And this periodic motion, we can capture it. Notice it's not doing anything else. And what's really interesting is we can get another one, and we can get two systems to interact. And in wave mechanics, we're going to find that there's actually only two stable solutions. So there's this one, and then there's this one. Okay, so in this one transfers its momentum into the other one, and in this solution, they both transfer into each other. And in fact here, we've come into a superposition of both solutions.
So in this demo, we're just thinking about how the world is basically just made of atoms, and it's all just vibrating. And this is a controlled way of demonstrating the different ways in which atoms can interact with one another and vibrate. Think about when you're heating something up, when something is frozen, the whole structure is being shifted by the fact that energy is being transferred between the atoms. And this is just an example of all the different ways that can be possible in our world, which is pretty crazy.
Then you see, because it's not in one of those two harmonic states of the system, it tends to move into the other states. So if you have if you have a particle and it's at rest, okay, then let's give it a kick, okay, and then it starts moving, okay. So there was a change in its velocity in a small time interval, okay, and so that impulse is known as an acceleration, okay. But suppose we wanted to have it change direction, okay, then that would actually be the original pulse plus another pulse, okay. So in other words, in order to rotate, even if the absolute value of your velocity, so your speed doesn't change, your velocity will have to change, okay.
Guys, this is really important.
Other pulse over here, okay.
We can just think of velocity like a bird flying through the sky.
And so what happens is, in order to orbit, okay, here's my massive object, a star or a planet, and then I move in like this. What happens is, I'm going to enter its orbit, and either I'm going to swing off, okay, like we do with satellites, or I'm going to find the perfect circle, and so I'm going to wrap around it and I'll keep going, okay. And so when I get that perfect curvature, in order to form a circle, then I get a periodic orbit. But most solutions are going to not look like a perfect circle. They're going to look like you're going to come in and then you're going to come off, okay? So the majority will look something like that, right? And so you're going to be flying off in all directions, and it's only when through chance that an object will then form a periodic orbit around another one, okay? But what does it rest on? Well, it rests on having enough energy that you can rotate around it, okay? But not so much that you end up just falling in and crashing. So, this brings us to an interesting concept in physics, which is that your acceleration is a measure of curvature, okay? And that curvature, we can even say more generally that in physics, you're either moving linearly or you're curving in some way, okay?
We can just think about this as a satellite orbiting Earth. So why does a satellite stay at its same point unless it's accelerating? It doesn't fall back into Earth, it stays, and it needs to be traveling at a higher velocity in order to travel to a galaxy or another planet or the moon. They require different speeds in order to be stronger than the gravitational pull towards Earth.
Linear motion or accelerations. So this idea of waves goes much further, So if we take this massive object, okay, and then we take another object orbiting it, then you get this classical motion of a planet revolving around another. But what if we said that the planet's motion itself was a wave, okay? So we could say that, let's bring the planet down here, and let's say that that's a spherical wave, okay? But what if...
This is an interesting idea.
Instead, we go further out in amplitude, okay? And then over here we go further in amplitude. Now that's not very symmetric, so what we would have to do is we'd have to do it again in the other sense, and then bring it closer the other way, okay? So now we have something more symmetrical.
He's saying that waves have to be symmetric, which we just saw on the graph at the beginning. Otherwise it doesn't work.
It's a demonstration of chaos, okay, and transfer of momentum. So that's why there's so many particles. But we just want to consider one for simplicity, okay? Now, this is symmetrical. It's centered about, you know, its own origin with respect to its string. But here, it's out of its symmetry. But there is still a symmetry, which is it always comes back to that same height on this side and on this side, neglecting the resistance. This is a bit old, so some of the energy goes out into the rest of the system, and so it slows down. But for the most part, you can see that there is a symmetry. So in other words, if we were to do this very weird thing and we were to take a planet, okay, and we have a satellite orbiting it, and then we say, but what if this is a wave, okay? So in this linear model, that would mean that sometimes the planet's here and sometimes it's there. So it would be like boom, 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 boom.
We can think about it going around half a crescent, so it's not that it's bumping into this one, it's just the position around that object that it's orbiting.
And so it goes boom, boom, boom. So now we're in 2 dimensions.
You can kind of think of it like a 3D drum.
Given 3, okay, so let's keep going. So let's get it totally symmetrical. So you have to imagine that there's this drum, okay, around the planet. And in its lowest energy, it's totally spherical. But if you give it a kick, it's going to go poof, right? There's going to be a dip in the balloon. The air pressure wave is going to come out the other side, and it's going to give it a kick this way, okay? So it's going to be then kicking under its own internal pressure.
So here he's just explaining the quantum atom. So it has its own harmonics. We think of an atom as just a spherical ball, but the whole idea with the quantum nature of the atom is that its energy levels are in waves. And so that is a much bigger picture of how things are interacting, how atoms are interacting in order to create the world around us.
And then on another axis and on a third. And then you could either get this, or you could get this behavior. Okay, so there'd be 2 harmonics. And this seems to be a more accurate description of the atom, okay?
It's a more accurate description.
Quantum atom. Why quantum? Because quantum means quantized. So it means that unlike a normal orbital, where you have a planet around a more massive object, right? That is going to, you can have it at any radius, okay? So you can orbit another massive object at any height. But what happens if you have this kind of drum phenomena is the radius is constrained, so you can't have any height.
So rather than just thinking of classical mechanics, which would be our solar system like model, where we've got the object and we've got the planet revolving around, we're thinking about the energy level, the wave levels of the atom, which is quite a lot more complex to understand, but that is what scientists believe are a more realistic model of what we're working with.
This going on with the wave, but then you could also have, this. So if this person kicks it really hard, then you could get this, but then you'd have to have the corresponding opposite, right, for it to be symmetrical.
This is a good way of imagining that.
Means you get a node in the middle, okay? So that means in the first one, we can have our friend skip in the middle, but in this one, you can have two, okay?
So the wave is affected by the two objects, or atoms in this case, that is transferring the energy. So if I have an atom here and I have an atom here, the energy from this side is going to have to be symmetrical with this side. So he's just talking about all the different variations of how a symmetrical wave could be.
We could have two nodes.
A node is kind of like our point of reference, the symmetry line that we're working with, as we now know that waves have to be symmetrical.
Which is this radius, r, okay? And we've managed to get the orbit to be quantized.
And there you have it, quantum mechanics in 20 minutes. Make sure to like, subscribe, and let us know what topic you want us to cover next.